Now we're going to talk about a special case of second order linear equations with constant coefficients. That is of the harmonic oscillator. And this is the model of a mass on a spring. So here we're going to have something like this. I'm going to have these constants here. We have m times the second derivative of y with respect to time plus a constant b times dy over dt plus k times y is equal to 0. Okay. And for the purposes of this discussion here with these harmonic oscillators, we want all of these constants, m, b, and k, to be positive. Okay. So now we're going to discuss the possible outcomes we can have from this discussion, this sort of situation. And looking at the polynomial, the critical polynomial involved here, the polynomial that we get here is m times lambda squared plus b times lambda plus k is equal to 0. Okay. So that's the polynomial. And so solutions will look like this. Well, the solutions of lambda is going to be equal to, via the quadratic formula, negative b plus or minus the square root of b squared minus 4mk divided by 2m. Okay. So now we're going to discuss what happens depending on the different possibilities for what we get out of this. Now recall, all of the coefficients are positive. So what's going to occur is what determines what happens here is what happens in what we call the discriminant, right? Whether b squared minus 4mk is positive or negative. So let me reset with the next slide, and we'll just talk about the different possibilities. Okay. The first one is if b is equal to 0. If b is equal to 0, this is called the undamped case. When b is equal to 0, lambda is equal to plus or minus the square root of 4mk times I over 2m. So here we get a purely complex eigenvalue. And this leads to solutions which are a sum of sine and cosine functions. We get no exponentials here. Okay? So it's an undamped spring. It oscillates forever. Okay? So that's what happens when b is equal to 0. Now, if b is not equal to 0, we have three cases. We have when b squared minus 4mk is negative, and then, of course, when it's positive or when it's equal to 0. But let's deal with the negative case first. So when what's underneath the square root in the quadratic formula is negative, then we get an e to the minus b over 2m times t in the solutions. Okay. So we'll still have those sine and cosines, because here we have complex eigenvalues again because the discriminant is negative, but we know that the real part of the complex eigenvalue is going to be negative b over 2m, which means there's going to be this exponential decay related to this solution. And this is called underdamped. And if you were to plot one of these solutions, it would look like this. Okay? So we are getting this exponential decay in the magnitude of the solution, but it oscillates back and forth forever. Okay. Now let's talk about what we have with b squared minus 4mk being positive. Here we get two distinct real roots. And this is called overdamped. What happens here is a solution might look like this. We just gently go towards the equilibrium position, or depending on the starting point, we might go above the equilibrium position and then go back down. So this is related to two eigenvalues that are both negative. This is a spiral sink type situation. You're always going to get negative eigenvalues out of this, and we have a spiral sink. And so you might go directly towards the sink, or we might go around a little bit as we go towards the sink. So that's what can happen when b squared minus 4mk is positive, and that is called overdamped. And then the last one, if b squared minus 4mk is exactly equal to 0, this one is called critically damped. And this is related to having only one eigenvalue. And when this occurs, we don't oscillate at all, ever, around the equilibrium value. We just go straight towards the equilibrium value over time. Okay? This is because in the phase portrait, we only have one line of eigenvalues that we can't cross. And so we can never cross the equilibrium. We're just drawn towards it immediately. So these are the four different scenarios and their names. So b equals 0 is undamped. You get solutions that never decay. They just oscillate like sine and cosine. Underdamped, you get solutions that decay, but they can oscillate. Overdamped is when the solutions decay, but they could cross the equilibrium solution, or the equilibrium point. And the last one is critically damped, where the solutions exponentially immediately decay towards that equilibrium solution.